we will start with a very important chapter in microfluidics, which is known as electrokinetics. So, electrokinetics is a very fascinating topic. It can effectively be considered as a full 1 semester course with electrokinetics in microfluidics. So, our objective will not be actually to get into all the details of electrokinetics, but to give you certain basic idea, basic motivation, and again how it can be used for biomicrofluidic applications. So, just like my other lectures, before getting into the subject, let me give you an example of why electrokinetics is important and how it is used. So, imagine that there is a microchannel made of glass. There is a saline solution, say NaCl plus water. Saline solution is very important in biological applications, all of us know about it. Salt is a very important component of the living system. So, now what we do is, let us say that we apply a field, for example let us say positive bias here and a negative bias here, and let us say that the surface of this channel has negative charge. What kind of charge it will have, how it will have, we will come to that later on. Just for the sake of argument, let us say that it has negative charge. So, once it has this negative charge and you apply this bias, you will see that there is a flow of this salt water from the left towards the right, if this is the arrangement. This is known as electroosmosis. So, why this occurs? To understand that, we have to understand a phenomenon called as electrical double layer phenomenon. Electrical double layer is EDL in short. So, what is this? Let us say that you have a surface made of glass. On the top of the surface, I am just not drawing a channel because another surface on this side will make a channel. So, I am just considering one of the surfaces. So, on this surface you have a saline solution. This saline solution will interact with the glass surface, and it may be possible because of very different types of mechanisms, that ion adsorption or forming covalently bonded surface groups, or several things can happen at the interface, that is essentially chemistry. So, let us not get into that in details. So, the surface may acquire a net charge. How much charge it will form or it will acquire? It depends on the pH of the solution. So, for example, for a salt water solution with neutral pH, that pH equal to 7, the glass will assume a net negative charge. So, let us put some 1, 2, 3, 4, 5, 6, 7, 8 units of negative charge, just as an example. So, this negative charge, therefore, it is not a sanctity, it could be positive, it could be 0. Everything can be played with the pH of the solution. If the pH is such that the potential, the charge here is 0, then that is called as point of 0 charge. There is no charge at the surface. So, let us say that this is the charge at the interface. So, when you have this charge at the surface, normal intuition is that whatever are the ions in the bulk, there will be more positive ions now, and they will have a tendency to all fall on the surface, but that does not happen. Only some positive will fall on the surface, let us say maybe 1, 2 as an example, they will fall on the surface. So, the surface has an effect, in effect the surface will be having net -5, and then there will be a, so this you have a layer of ions on the surface which is adsorbed on the surface, and this is called as Stern layer. So, there is a fixed layer of ions which is there on the surface, and this does not move. On the top of this, now what will be there? So, you expect that there will be more positive ions than negative ions, and in fact it is like that. So, this layer has 4 positive, then there will be a layer with 3 positive. I am just giving some arbitrary example. Just like that, you will see that there will be more positive. So, this layer, this has total 5. So, let us say the total remaining will be +5. So, this will have +2, then let us consider it +3, then maybe +2, so in this layer you have 1, 2, 3, 4, 5 -2, that is +3, and in this layer +2. So, total +5 and -5 makes it neutral. So, this is a hypothetical picture, do not think that this actually happens. My whole idea is to give you an impression that the surface has a charge, the bulk fluid will have the opposite of that charge to make the system electrically neutral. So, when it is happening like that, because of the charge difference between the positive and the negative charge, there will be a potential developed across this. So, now you can divide this region into 2 parts. One part is the layer of ions which is fixed to the surface and it does not move, this is called as Stern layer. Above this dotted line, this layer of ions, few layers, these layers will move depending on the action of whatever force is acting on this. So, this is called as a diffuse layer or a Gauss-Chapman layer. So, the charged surface with this charge layer together is called as electrical double layer. Okay. So, now in order to drive the flow in the axial direction, we must understand that what is the potential that is developed across the electrical double layer. So, our objective next will be to find out the potential distribution within the EDL. So, the very important parameter that we consider for finding out the potential distribution is something called as electrochemical potential. Electrochemical potential is a combination of chemical potential is relatively well understood in thermodynamics, and let me briefly tell you what it is. So, chemical potential signifies physically the driving force for a chemical change to take place. So, a system in chemical equilibrium means that there is no gradient in chemical potential. Now, in this system you have ions. So, ions are not just chemical species, ions have also charges. Because they have charges, they respond to electrical field and they have an additional potential which is electrical potential. So, combination of electrical potential and chemical potential is known as electrochemical potential. So, we will calculate what is the electrochemical potential of a system where you have a solid surface and let us say y is the direction perpendicular to the surface. So, the chemical potential, so let us call it as mu. So, mu naught is a reference potential, Kb is the Boltzmann constant which is the universal constant, that is 8.314 kilojoule per kilomole Kelvin divided by Avogadro number. So, Kb is the, let if we call R as the universal constant, R with a bar at the top, divided by the Avogadro number. That means if Avogadro number of species are referred to this particular constant, then for each of these species, that is for each entity, what is that corresponding constant. So, Kb into T into ln of n, where n is the number density or concentration. So, where from this comes? Let us quickly revisit something in thermodynamics to get a conceptual understanding. All of you have an idea of what is Gibbs free energy. This is something what you have studied in basic thermodynamics. So, Gibbs free energy is given by H minus Ts. Now, what is H? H is the enthalpy, T is the absolute temperature and S is the entropy. So, free energy is the energy freely available for a change. Just let me give you a very interesting example. You know, in human life, which state has the highest free energy? The highest free energy is associated with the birth. The reason is that the entropy associated with birth is very low, because entropy is associated with the probability of occurrence of the event, birth is much less probable than death. Death is inevitable, but birth is much less probable. So, entropy associated with birth is very low. So, the free energy at birth is very high, and then as you grow older and older, you consume that free energy for your overall growth, and you eventually come to a state when you go towards your death. At your death, the free energy becomes a minimum, and then you come in equilibrium with the surroundings, so that you have no further change that is possible in your life. So, very similar thing happens in a chemical or a electrochemical system. I mean, human life is a very complex chemical or electrochemical system, but even in a simple system the same thing happens. So, dG is equal to dH minus TdS minus SdT. Now, you have a identity in thermodynamics, TdS is equal to dH minus VdP, where V is the specific volume and P is the pressure. So, dH minus TdS is VdP. So, dG at constant temperature is VdP. For an ideal gas, PV equal to RT. So, dG at constant temperature is sorry okay. So, this pressure is a quantity for an ideal gas which relates the free energy with the temperature, universal constant, etc. Now, if you have instead of an ideal gas or a real substance, this pressure is replaced by something called as fugacity, and if it is a mixture of entities, then instead of a fugacity of a single component, it becomes a fugacity of a component in a mixture. And for an ideal solution where there is no change in volume due to mixing, the fugacity becomes so this fugacity expression eventually boils down to the mole fraction or the number density. It is of course it takes a little bit of length to go from here to here, but I have tried to give you the conceptual paradigm that essentially this is for an ideal gas, but if it is not an ideal gas and if it is a component in a mixture, then this pressure is replaced by a pressure like quantity called as fugacity. For an ideal solution, it boils down to the mole fraction, which is the N here. So, let us write a fresh expression for the electrochemical potential. So, you have mu equal to this is the chemical part, there is an electrical part. So, this is the electrical component. What is Z? Z is the valency, E is the charge of a proton and psi is the potential. So, the electrical potential is, so this is basically electrical potential is given by the potential times the charge. Okay. So, now you have for electrochemical equilibrium okay. So, now let us say at infinity, infinity means far away from the solid boundary. So, at infinity means far away from the solid boundary, the effect of charging of the wall is not felt. So, at infinity you have psi equal to 0 and n is equal to n0, which is the bulk concentration of the species. So, n refers to the concentration of that particular species. So, for example, we can give a symbol n plus for Na plus, n minus for Cl minus, like that. So, it is a generic n which could be positive ion, negative ion, whatever. So, you have KBT okay. So, this is called as Boltzmann distribution. So, this does not tell you the potential in the ideal, this tells you how the potential is related to the charge of a species. So, if you consider the potential, see, because of negative charge the potential here is there, and then the potential will go to 0 asymptotically, at infinity it will be 0. So, now if you think of the electrical double layer, you have the Stern layer like this and the diffuse layer like this, whatever. So, this demarcation between the Stern layer and the diffuse layer, this is called as shear plane, and the potential at the shear plane is called as zeta potential. So, here you have psi equal to zeta. This is a very important symbol or very important parameter in electrochemistry. This is called as okay. So, now this does not complete our system of equations. Why this does not complete our system of equations? The reason is that we have related the potential with the charge, but we need another equation to close it, because here there are two variables, one is psi, another is n. Okay. So, the other equation is provided by a very fundamental consideration in electrostatics called as Gauss law. So, what is Gauss law? I will explain the meaning of each symbol. Epsilon naught is the permittivity of the free space, E is the electric field, ds is a surface element. So, if you are making a dot product of electric field with the surface vector, this surface integral over the surface S is as good as this volume integral. This is the total charge density, that is charge per unit volume times dV, where V is an elemental volume integrated over the volume which is enclosed by the surface S. So, Gauss law essentially relates the charge density with the electric field, and that is how the charge is now being related with the electric field. So, with this we can say that the rho E total so this is volumetric charge density. Total volumetric charge density. Charge density, volumetric charge density is charge per unit volume, surface charge density is charge per unit area, like that. So, rho E free plus rho E bound. The bound charge density is given by the minus of divergence of a vector called as polarization vector. It is essentially the dipole moment per unit volume. So, this P is constitutively related to the electric field by the following. This is the relationship between the polarization and the electric field. This is how fundamentally the charge and the electric field are related. So, this chi is called as susceptibility of the medium. Okay. So, now and this rho E free is often given a symbol as rho E. The free subscript is often taken off with an understanding that charge density here we write as free charge density. Bound charge density is taken care of within the expression itself. So, you can write epsilon naught In the next step what we will do is we will use the divergence theorem, that in place of this surface integral we will write equivalent to the volume integral. So, this was attributed to Gauss, and that is why this is also known as Gauss divergence theorem. Okay. So, now because the volume element is arbitrary, we can write So, we can write okay, just taking this here and taking epsilon naught inside, it does not matter, it is a constant, it is a permittivity of the free space. This is defined as epsilon r, which is called as relative permittivity of the medium. So, and epsilon naught into epsilon r, if we call as epsilon, then we can write this is called as the Poisson equation. Why the Poisson equation? Because E can be expressed as minus of gradient of the potential. The electric field is minus of the gradient of the potential. So, this is called as Poisson equation. It is a prototype equation in applied physics or applied mathematics, where you have the Laplacian del square is equal to something in the right hand side. If the right hand side becomes 0, it is called as Laplace equation. So, now we have two equations in hand. One is the Boltzmann distribution, another is the Poisson equation. The charge density can be expressed in terms of the number density of charge, that is n plus or n minus, and using these two we can get a unique equation, the Poisson equation and the Boltzmann distribution. Using these two we can get a combined equation which is called as Poisson-Boltzmann equation. In the Poisson-Boltzmann equation, the potential is the only variable from which the potential can be solved. How it can be solved and how that can be used to assess what will be the fluid flow inside the channel because of electric field, that we will study in the next lecture. Thank you very much.